So I guess I will get started here. Let me know if there's any bad signal or other issues. But what I really wanted to do today was just do a bit of kind of basic demystification of of kind of what LLMs are in terms of like our kind of like what are the useful ways to think about them, what are their constraints and so on. We're not going to be diving into like their individual technical architectures. Um, and the reason we want to do that is that we want to be able to contextualize LLM models within the systems where we find them, right? Something like ChatGPT or our KMS conversational interface. Um, and so let's get started. So I wanted to start with just touching on kind of what the materials in quotes are of these LLMs. Um, and the first important thing here is that we like to talk about LLMs as interacting with language, but it's important to remember the caveat that we're actually talking about the digital representation of language, right? So this is a total ordering of character codes or a string, if you will. So this is the kind of underlying material that it's working with. And then on top of that, and this is actually what the LLM is generating, is tokens. So you take some number of characters and you group them together. This is not a manual process. This is kind of a process optimized for LLMs. There are many ways to tokenize a string. This one here is from OpenAI. So you can see, for example, that a colon is its own token because it kind of wants some independence with the ability to generate that. And yeah, these are the kind of the basic units that are actually being generated. So the next thing is context windows. I've left some citations in these slides as well, which I can link to later. So it's important to know about context windows, right? And what they really are is just the kind of input space of an LLM. So a context window defines kind of the maximum amount of text that you can give as input. And every system so far uses these context windows to kind of to work with LLMs. And we'll get to how you can do that later. But where I wanted to start is to note that that the kind of the reason to have these hard cutoffs for context windows is often not defined by the LLM models, but it's basically their performance over varying lengths of context. So for many models, there will be a point where the quality basically starts to deteriorate. And so the people that have made the model will be like, okay, this seems to be about the right place to draw the cutoff line, because using more than that is going to deteriorate the quality. And so we want quality, even if we sacrifice some extra text that you can give as input. The second thing here is the position of a token in that context window affects how the LLM uses it, right? So in this example, this is looking at embedding, or sorry, I should say, a kind of using bits of text from documents, and then how accurate it is in its responses based on the position of that document, which you can really here just think of as a string in the context window. And so we can see that stuff way at the beginning tends to be more accurately understood, if you will, than stuff in the middle. And the same is true for stuff towards the end. And this is a shape that we see with a lot of LLMs. I'm sure that this will change over time. But yes, depending on where you are in the context window, that will affect the performance of the model. So the next thing here is around models of reasoning, and specifically looking at the ways to kind of replace the inner workings of an LLM, but have the same apparent structure from the outside. What I mean by that here is that we can think of each of these models as really just like a function that takes text in and text out, right? Like it takes one big chunk of text in, one big chunk of text out. But within these models of reasoning, that we can actually have multiple calls to LLMs. We can do other fancy stuff, but in terms of using these within a system, your kind of use of them is essentially equivalent. Um, so here are some examples, right? The one on the left is the kind of the classic send some input to an LLM model, get some output. Um, we can do chain of thought prompting or chain of thought reasoning, where you're basically asking the model to kind of take a few intermediary steps before you get to the final output. And more recently, we've seen this kind of research get a lot more varied and interesting with this kind of self-consistency model, where you're basically exploring multiple possible paths and you're voting on which ones seem like the best ones. Or one of my favorite recent ones is this tree of thoughts model, which takes some of these same ideas, and it does some really clever kind of evaluation on like what are the likely paths to succeed, which ones seem kind of doomed or flawed from the get-go, and it's evaluating these against each other, these little like thoughts as they call them in the paper. And then at the end, you still have the same thing, right? So the outside perspective is always just you give it some input text, you get some output. But what happens in the middle, it can vary a lot, and that will drastically impact the kind of apparent reasoning abilities of these models. Yeah, here are some citations for those, and it's worth noting that like we can quite easily imagine other models. Like, for example, you could imagine a graph of thoughts, which was actually suggested as well in the tree of thoughts paper. The structure is always the same, right? It's text in, text out. But there is a lot of kind of very basic exploration to be done in discovering what models are effective, right? Most of the stuff that's happened so far is not exploring particularly radical ideas. It's just doing stuff that no one's got around to researching and publishing on yet. So we're going to see, I think, a lot more of this in the future. So the next section here is around one way that we can shape generation, which is guided generation. And this is the process of conforming the output of LLMs to schemas, structures, or syntax, right? For example, if you want valid JSON out the other side, guided generation is probably what you need to do that. And there are a few different ways to do this, which we can get into now. So the most common and easiest in many ways is just to use prompts, right? So you can say, give me the response in a numbered list. It will probably do that, and you can probably pass out the list from that response, but it's inherently brittle kind of due to the probabilistic nature of these models. And so other approaches which kind of guarantee some robustness, for example, using context-free grammars, where you're basically limiting the valid tokens to continue like a sentence to a syntax or a grammar that you have defined. So you can do a lot of complex stuff here. Like, for example, you can take a grammar of a programming language, say Python, and you can guarantee that the output from the LLM will be syntactically valid. It doesn't mean that it's going to do what you want, but you can at least guarantee that the structure meets this grammar, and that's really important when we are building systems that involve kind of parsing or interpretation of textual output. If we can lock down parts of their grammar, that means that we can not worry about these parsers failing even a very small fraction of the time. We really want kind of strong guarantees here. One example of this is JSON former, which basically fills in the fixed tokens, like the kind of structure of JSON, and then you're only generating, you're essentially filling in the blanks with the generation process. So this guarantees syntactically valid JSON. It actually speeds up the process a lot because you're skipping generation of quite a few of these tokens. And it lets you kind of move data around between parts of an LLM system without having to worry about some missing quotation mark, breaking your whole system. Okay, so the next kind of way that we can shape generation is through these approaches of augmented generation, which is really just ways of building a context window for the input. So you can see this, for example, in the KMS chat interface that we have now. You'll give it some input, but then behind the scenes, it's going to go off and query a database, pull back some text, and then it's going to build this kind of structured context window. So you're taking a small bit of input to drive the creation of a much larger input behind the scenes, which is what goes as that single piece of text to the LLM. So retrieval augmented generation is like the most well-known popular task for this. This is what we do with querying our knowledge base. And again, I'll link to all of these papers later. Yeah, so this is our system. We won't go into it much, but you can see in this step here, creating a prompt. That's really kind of where this is all coming together, right? So you have your chat input from a user, but this is then combined with a bunch of other elements to kind of form this prompt, which then becomes the single input to in this case a GPT model, right? And that's how we are able to do things like this, where we can ask about GDS and it knows that GDS is talking about generalized dynamical systems, which it will not be able to do if that context is not provided behind the scenes, because it was not kind of sufficiently represented in the training data. So another approach is this quite big category of approaches, really, which is tool use. So we can imagine this as taking kind of intermediate outputs of an LLM, and instead of giving the output directly back to a user, we're instead noticing like a pattern in it, and we are then passing some of the output there. We're delegating to a tool through whatever means, right? It could be a like a Python REPL, it could be an API endpoint, doesn't really matter. And then we're taking the result of that and we're kind of formatting it in a way that's suitable for the LLM, passing it back to the LLM, and then letting it continue. This, in principle, can do many, many steps, right? It could use a bunch of different tools to solve a very complex problem, but we're absolutely not there yet. And there's a lot of challenges with stopping it from going way off track or getting stuck in kind of loops. And we don't have particularly good approaches for allowing humans or other agents to influence this kind of multi-step process that LLMs are doing. Although I suspect we'll make a lot of progress there quite soon. Okay, so those are some of the ways that we can shape the actual output of an LLM. The next kind of big section here is really about LLM systems, because I want to kind of disambiguate LLMs in the sense that something like ChatGPT is really it's a long way from being just GPT with a text box attached to it. And so to get into this distinction, I wanted to break down two of the most important parts of many of these systems, although far from the only ones. So the first one is embedding functions, and to build a bit of an intuition here, an embedding function will take some data, right? In this case, it is audio recordings of from seismographs, and it is then assigning those to a point in space, which is the embedding space on the right here, such that distance corresponds to something meaningful. So we can see here that these two orange dots are very close together. I assume in the original context that means that these were both likely to be kind of seismic events or earthquakes. But we don't have to do this just with audio. We can do this with images. So this is taking handwritten numbers, and it's assigning them to a position in space such that If you take any one of these numbers and kind of look at what's around it, you are very likely to find another image that is the same number. This here is represented in 2D. This is a T-SNE diagram. But the reality is that these are actually very high dimensional. Our system has an embedder that I believe uses 768 dimensions, but that is 760 something more than we are able to visualize on screen. So hopefully this kind of 2D representation can give you a good intuition. And here it is again with words, right? So we can see, for example, that like we have this cluster of numbers. We have some of these kinds of grammatical parts, right? Of like no, not, or, there, this. We have stuff that's I'm not quite sure how you would describe this cluster, but it's bad stuff, I guess, right? Heart abnormalities, coughing, pain. These are things we don't want. And so in this way, we can cluster things up in a way that would be extremely challenging to do for a human. But embedding systems have become quite remarkably good at this process. So yeah, so one example of this is Instructor. This is the model that we use for embedding. It's actually a prompt-driven system, so you can actually fine-tune how you're doing those embeddings with a prompt, right? So we can, for example, focus more on clustering related kind of academic ideas together versus kind of the different intended audiences for language, that kind of stuff. There's a lot of flexibility here that we haven't explored, which we'll come back to in the future. So vector stores, which is a word that I definitely chuck around a lot, but these are really just databases for vectors. And they give you efficient ways of querying by distance, which is basically our metric for similarity, or the distance encodes something meaningful. Okay, so most LLMs are actually made of multiple parts, right? So ChatGPT is what you might call an LLM system. It's not just a GPT or LLM model. And so ChatGPT is using augmented generation approaches, using your kind of past messages to give this appearance of having a memory. There's a very good chance at this point that it is using embedding systems as a part of that process, so that it can compact a potentially very large message history into a space that can fit within the context window. Because currently the context windows are really in like the tens or low hundreds of thousands of tokens, which is big. In some cases, it's maybe a book, but it's not like it's able to look at your entire file system at once, for example. So there's a lot of different ways that we can kind of include LLMs into systems that we are designing, right? Like this list is probably not a great one, but some would be, summarizing, translation between languages or context. By context, I mean that maybe you want to take this very kind of technical idea and translate it into like a more casual context using analogies and things like this. We can use LLMs to augment existing interfaces, and we'll get more into that in a second. And then we can do things like classification, categorization, ranking, and evaluation. And especially these last ones here, they really let us build much more kind of complex systems with LLMs that have a higher degree of apparent intelligence, because things like ranking and evaluation can be kind of applied to the outputs of the LLM itself. So we can use it not just to evaluate or rank things that we do, but we can use that to kind of self-evaluate in these systems. And this list could really go on for many pages. But the point here is that the role of an LLM in a system doesn't need to match the pattern that we have, for example, with ChatGPT, where it's going to give you some output back. It can also be kind of somewhere in the background doing things that are incredibly useful to us, but that might not be visible, at least not, yeah, that might not be visible. All right. So I think this is one of the last sections here. So I wanted to touch on interfaces, because as we've kind of seen, there's a lot of ways that we can use LLMs in these systems. And a part of what kind of shapes our kind of collective imagination about what LLMs are is how we interact with them. So there's chat. Everyone knows this, so I didn't bother including a slide. But you type some message in a box, you send it, and then you magically get some text back. And this is great, right? This was really the one that took off and have made waves and changed a lot of people, or how a lot of people view this technology. So another one here is kind of this broad category of what you might call like diagrammatic representations. So constructing things from blocks, wires, directed acyclic graphs, and so on, lets you build things that might look more like kind of workflows or signal processing chains. But instead of, for example, audio data, these can be using kind of streams of natural language between LLMs that are doing different kinds of things or different kinds of processing on that language. So yeah, we have these kind of signal processing type approaches. We have kind of spatial encoding of semantics. So here, I think that the text is a little bit too small to see, but what's happening is that distance is encoding a change on some described dimension in natural language. So, for example, you kind of start from a quote, which happens to be this website uses cookies to ensure that you get the best experience on our website. But then you can say like, okay, let's make this 0.83 times longer, or more artistic, or more sci-fi. I've seen people have a lot of really great fun with these systems. And the point here is really just that there's a lot of ways to kind of to represent the kind of semantic affordances that we want, that we can use to interact with these LLM systems, and encoding, a kind of dimension in the actual kind of coordinates of a canvas is one of the many ways of doing this. The last category, and this is really the biggest, or I hope it will become the biggest, is various forms of interface augmentation. And so just to pick one example of this, I believe that this is Notion. The specifics aren't particularly important here, but the idea is that, let's say that when you right click something, right, when you have these context menus and you've pointed to something, say on screen, like a piece of text, there are potentially a very large number of things that you can do, right? Like ways that you can act on or with the object in front of you. But because we don't want to force people to kind of scroll through impossibly big menus, at the design step of software, we will usually kind of put a lot of thought and effort into shrinking the list of possible actions down to the ones that we think people will need, and we end up with these kinds of pre-designed context menus. But LLMs open up the door to, for example, taking a list of 1,000 actions that are kind of admissible in that context and shrinking it down to, some small set of likely actions. So there's a lot of ways that we can kind of augment what you are working with on screen, in ways where the actual kind of textual output from the LLM is invisible to you, because you're essentially using it as a kind of natural language reasoning system, as part of, for example, a piece of software, as in this slide. There are two references here. Linus Lee is the one I actually stole this slide from, so he gets credit for that. Geoffrey Litt, who's done some work with a group called Ink and Switch, they have this kind of approach to taking like a textual document and incrementally augmenting it with computation. And so most recently, they've been using LLMs to kind of build bits of computation into your documents and do very kind of nuanced forms of pattern matching over a document, which is again a way that kind of makes the LLM itself somewhat invisible. Cool. So the summary here, we have the materials of LLMs, which are tokens built of digital text. The context window defines the input space of an LLM model. Guided generation is the process of conforming the output of LLMs to schemas, structures, or syntax. Augmented generation is a way of automatically constructing a context window, usually around some base input, like the message that someone is sending to ChatGPT. Text embedding functions maps a string to a position in vector space such that distance encodes some meaning. Very often, this is something that resembles semantic similarity, but you can encode other things as well. And then vector stores are just databases optimized for vector data, which is very useful because that is what you get out of an embedding function. So usually an embedding function and a vector store, they kind of go hand in hand. Okay, so some last thoughts here. So if we're careful in identifying what LLMs are and aren't, along with their limits like token windows, and looking at how we can compose them into other systems, we're in a much better position to understand and design systems which leverage these new capabilities, and also to kind of not let our understanding of what the LLM model is from drifting with the ways that we experience it, like for example with ChatGPT. So really to separate these two. There's a very vast and unexplored space of UX and interface design. We've really just scratched the surface of this. And I think the single key takeaway, for me at least, is that LLM models are not the same thing as LLM systems, and it can be very useful to kind of distinguish those, right? So GPT is not ChatGPT. Our KMS conversational system is also not, the GPT model that sits underneath it. And yeah, I think that is maybe the last slide. Let's find out. Yeah. All right. That's all I have. And I will stop sharing my screen.
Nice job. Thanks for putting that together.
Yeah, no worries.
Yeah, that was good. Very useful.
Cool. That's the goal.
And one context, local sort of local question with local context to one of the slides, the augmenting with tool use.
Yeah.
And you said that there are sort of problems with the systems using this technique going off the rails.
Right.
What are there any sort of comments you can make around sort of the conditions under which rails are left, or is it too soon to say?
Yeah. So I think the biggest challenge that we face is not having sufficient ways to guide some more long-lived process or to kind of to intervene. So for example, we can build systems that will produce plans and strategies and do self-evaluation and all of these things. But what will happen kind of through the course of that is that they might make a plan which is kind of mostly what you want, but then in the execution, they'll kind of end up going down a tangent, and they'll be evaluating it against not your view on whether it's the right thing, but on some kind of slightly imagined view. And so the kind of you get this kind of drift from what you originally intended to what it ends up producing. We can go a really long way with better kind of self-evaluation approaches. There's like AutoGPT and MetaGPT are two popular examples that do some of that. But what neither of those have, at least the last time I looked at them, were kind of like robust ways to be a kind of guiding influence in that process.
Me specifically of what Octopus was discussing in the artificial life evolutionary algorithms discussion, and the notion of feasibility and the like models of the world, and needing to refine or adjust the models of the world in addition to the behavior within them. And I mean, I won't try to recap all of that. I think we have a recording and some notes that he shared. It was from the Econ Pod. But I think very concretely, from a control theory perspective, what you described implies a need to impose more structured models. So, like, if you want to build a system with the intelligence that has actuators, sensors and actuators through a tool, then you need to put a more robust, less self-learned model of what is desirable in place. Otherwise, in some ways, that adaptivity becomes a liability. You need to be more careful and more forward about asserting the things in the computational system, the representations of what is good as well as what is not okay. But that inevitably means taking a step away from these sort of totally quote unquote model free models towards things that have more again, more work on the upfront by the people putting them into production, because they actually have to model. They can't just be like, I want something like this, figure it out.
Right. And I think that that's reflected in that we've been able to build reasonably complex reasoning models that are more specifically purposed towards a task. If you already have enough of that, then they can potentially do a very good job. But if you want to build a kind of generic reasoning system that lets, for example, someone just ask something in terminal and have the system go and figure it out using all the tools at its disposal, that's a much kind of harder problem that we're only just starting to get to.
It seems to me that some of this is also just like misunderstanding on the part of people. And I say this I'll take it somewhat philosophically. There's this notion of the fundamental problem of communication, which is to say you have a thing in your mind that you want done, and you have another thing, which is the computer system that could potentially do it for you. It's only going to pursue its understanding of what you asked it to do in the best case. And in the worst case, you have a principal agent problem. But let's imagine we're still in the best case, where it genuinely has no problem with pursuing exactly what it thinks you asked it to do. Its ability to do it is still bottlenecked on your ability to have, let's say, the same understanding of the thing to be done. And by definition, people are saying, I don't want to have to tell you, figure it out. But just doing that already means that it just might be insufficient. Like, it just might not be informationally possible, because at best it's going to do what it thinks what you meant, and it could get really good at inferring from a lot of the other contextual information. But even if it does, you haven't eliminated the problem. You're just sort of hacking your way around the quote unquote fundamental problem of communication. There's no solution whereby your agent does the thing for you that you wanted, only the thing that it perceives you to have asked it to do. And there isn't ever going to be a perfect mind meld there.
Right. And I think that's part of why the solution needs to involve kind of ways of kind of reducing the surface of what you need to give as guiding input. So right now, a lot of the systems, if you wanted to intervene, would require like a large amount of manual work and like writing a lot of text. And if we can't have, for example, a single sentence be used as input to get like the answer that you want, we would like, for example, that it reaches some point and it's like, oh, actually, I need more input here, but I'm not just going to pause everything and ask the user to adjust all these knobs. I'm going to just ask them like a condensed question that should give me the information that is needed, so that you can kind of guide it with less information.
Yeah, well, no, I mean, I think maybe the question isn't even whether it's less or more information, and more about whether it's like the right information. So, like,
Right.
imagining that you've got a really big, an interface that's capable of expressing a lot, but a lot is, you don't need a lot. You need the right stuff. And so the question is like, how do you figure out what the right stuff is? How do yeah, I mean, this is also like kind of a long, we don't need to go too far down this tangent, but I'm just thinking about it from a almost like robotics perspective, where what you want is a a corporeal robot, one that has sensors and actuators, but it has, so it can act on the world and sense, and you need to tell it what it's optimizing for, subject to what constraints, over what time horizon, yada yada. It can't function without those things. So whatever you tell it is ultimately going to result in some kind of inference or underlying model of those things, and then it's going to act pursuant to them. And the idea that the something like goals and constraints needs to be more stable than, say, your estimate of the state of the world. Like, there's a sort of a temporal frequency domain thing going on here that at least I feel like is sort of required in order for these kinds of agent systems to work. You kind of want it to, you want to solve for the interaction of, okay, we agree on what you're supposed to do, as separate from like your effort to pursue it. Like there's a and maybe that's not helpful, but my gut is that, like, as long as you're trying to collapse those two things into the same like process, you're gonna run into issues, because then the system is just as likely to adapt what it thinks it's trying to accomplish as it is likely to adapt what it thinks the state of that effort is, which is not a good way to get something done.
Right.
So yeah, anyway, so there's certain like modalities that exist in existing automated systems, physical ones, that I think could be intentionally enforced in architectures, modular, like intentionally modularizing, enforcing different components with different purposes, and then letting the individual parts solve for their own bits, potentially in a dynamic way, but while enforcing that architecture, say.
I think that seems right, and I think it is reflected in the best efforts that we have so far. Like, we see quite a strict separation, for example, between planning and execution, where you can kind of intervene at the planning stage, and then you kind of delegate parts of that plan to these more agentic systems.
Right. And I mean, in general, for robotics, like this sort of, I can zoom out. I mean, you have SLAM, which is simultaneous localization and mapping, but that presumes some world model. So you kind of have a ontology, or kind of like a world model of some kind. You have simultaneous localization and mapping as a set of paired processes. You have goal setting. You have path planning. You have kind of navigation, which is kind of trying to move along the path. And then you have things like low level actuation. And like all of those are actually effectively happening at the same time in some systems, but they have different they have specific codependencies on each other, and they have very different purviews, and they also have different natural timescales.
Right. Yeah. I wanted to make sure to leave time for like a round robin, as David mentioned in the beginning. So maybe we can go around and give updates. I feel like I don't need to give one, so I guess that's Josh and Emmanuel.
Oh yeah, so see you all next week.
I will see you
Your
next week.
Oh yeah, I'll give an update. Actually, let me just show you. Yeah, good presentation. All right.
Thanks.
Oh, shit. All right, so yeah, right now, in this POC, I finished the structure. Okay, so the structure is represented as a Python object and um, intended to be a part of an executor that the factory produces. So AKA I'm working on the factory, right? So I have a means of creating structure. Right now, I'm writing the API for function quickly because I'm getting prepared for an ingest. Okay, so I'll just run what I have. And I have it integration tested as well. So let me just run something for them. So this is a Python module that is going to instantiate the infrastructure portion of what you saw in that diagram. So there are resources on my cluster that I just auto destroy every time I run. So it's initializing, Terraform's initializing. Okay, so these are some Terraform resources that are being created. The first one, I'm deleting the previous cluster. The second one, I'm setting up COD. That's installation that goes in. That shouldn't be in here. I'm just doing it for convenience. Now this one isn't. This one is the Kubernetes cluster. Okay, that's created. It takes about 22 seconds. And all this is in the Terraform file. So, all right. But in the meantime, I am considering some network bottlenecks for ingestion. Okay. So after I'm done with that module, I'm just going to do the ingestion with COD, which I already have a plant written for. Why is it? Am I saying the right thing? Hold on. Okay. It's misprinted. Hold on. Okay. So this is the Kubernetes operator for the Kubernetes cluster. This is the HDFS cluster. Hold on, let me see. Hold on. It errored. Hold on for a second. How's it running? Yeah. Something's wrong with my terminal. It froze. Okay. Let me just try to do one. So yeah, that was an error message that the apply didn't work. The instantiation of the infrastructure had an error. Okay, there we go. That's wrong. Should take that out of there. But yeah, in the meantime, the network consideration I was having was it takes a long time to retrieve things from Filecoin from a pinning service, which is a service that hosts your data to be bidded on for storage by Filecoin storage providers. And there's criteria for them to be considered bona fide Filecoin storage providers in the protocol, right? The pinning service I'm using takes about 48 hours. So if I put data on there, I guess, propagation over the network or redundancy is valuable in a peer-to-peer data, in a peer-to-peer storage scenario, because there's more availability. It should be there are more pairs that there are more pairs that could host that, because there's more availability, it's easier to access the data on the network. So it's within your best interest for it to be hosted by multiple false coin storage providers. So what the fuck? Hold on for a second. In other words, if there was a, let's say, a parallelized ingest, I don't want there to be network latencies. So all COD does is open multiple threads and make network requests over them, right? So it's waiting for the job to complete in each thread. So if you submit, I don't know, 8 jobs, which could be 8 partitions of a data set, for example, or just an entire data set, it doesn't matter. You have to wait for the job to complete, which is contingent upon the network enabling somebody to access the data, which isn't guaranteed, because there's no guarantee as to the availability of the host, which are the pairs on the network. So the more pairs has the same file and hosting it, the better. So I have to figure out a means of smoothing that. And oh, it worked. Okay, let me try it again.
Question I have is that we've heard from multiple sources that IPFS has performance issues. So
Right, but I think
are we just running into that?
Well, I'm not. Okay, I operate IPFS myself, and I don't have any issues.
Okay,
Why?
so
Because
this is a private cluster thing?
I'm not worried about IPFS itself having issues, because I never had an issue once I used the addresses of the client, which I am publishing. The problem I'm having is these providers, they're not going to publish that. That's a security concern. That's literal money it's like, if they publish that, that's free money. So they're not going to publish that. Okay. So in the event that a client appears on the network and they're publishing to the network, it's within the best interest of people accessing that data that more than one pair has the same file. It's kind of like back in the day when you were using peer-to-peer networks, seeders and leechers. That's it. Okay. That I can trigger redundancy of the same file, right? So the degree to which I do that depends on the structure. I would say I'm CIDing I'm CIDing a document, which is the bomb. Okay. That is just for the executor in this diagram to not have to do network calls, right? Unnecessarily.
Thanks, Orion.
All right, thank you.
Yeah,
Right.
Okay.
Right. That's just for the executor not to do network calls unnecessarily, right?
Mm-hmm.
But what the final CID will be is just a directory. Okay. That's put on. What's going on? Okay, I'm getting rid of IPFS. I'm sorry, I'm getting rid of HDFS. Sorry about this. I don't know why this isn't working. Okay.
No, don't worry about that for now. We've got we know what you're working on, and it's a work in progress.
Okay. Okay. The reason my workaround for this, okay?
Yeah, I was gonna say, we gotta jump, Emmanuel, you've got a call coming up. We'll go over, CAD's, the status there.
Part of that discussion also needs to talk is preparation for having, we have a call in maybe an hour after that, or we have a call later with somebody who might be interested in contributing to CAD. So we're going to want to, in part, talk about CAD, both the status and also prep for our call with the Ansel.
Yeah, so let's break here. Josh, you and I touch base. Do we have a call at 4 today?
Oh yeah, we have a call for. We'll talk about this later. But
Yeah,
let's
let's hit status there. We'll shift over to the CAD call and get ready for that stuff.
Right. Have a good one.
Cool. Thank you all.
Everything is on network. That's all I wanted to say. Like everything all here was processed on the off of the IPFS network. So anyway, I'll talk to you later. Bye.
Yep.
Thanks all.